Hi, I'm Xiaozhen Huan, and I'll be introducing the system design of ICDSS, Intelligence Clinical Decision Support System. ICDSS, the Intelligent Clinical Decision Support System, is a hybrid clinical reasoning architecture designed for explainability. Rather than relying on a single black box model, the architecture decomposes clinical reasoning into three independent tracks: deterministic, statistical, and cognitive. Running on top of a Dockerized stack, in this video I'll walk through the system design, the data flow, and how each technical use case maps to a specific layer. The architecture. The system runs as three Docker services orchestrated by Compose. The first service is the Streamlit application, the orchestration layer. It hosts the dashboard, coordinates the three reasoning tracks, and renders the interactive knowledge graph using Streamlit AGraph. The second is Neo4j version 5.26, the knowledge backbone, loaded with graph data science, GDS, and APOC plugins. It stores both patient graph and the clinical knowledge graph and supports our similarity computations. The third is Llama, serving Llama 3 8B, the distilled version of Llama 3, locally on port 11434, used for symptom extraction, PDF triple extraction, and rationale synthesis. All three services communicate over a private Docker network using service name DNS. And also it comes with the entire stack with health check before startup. Data pipeline. Data flows through a 5-step pipeline implemented in data pipeline. Aggregation. CSVs from UCI heart diseases dataset across 4 medical centers are merged with column standardization via column map dictionary. Synthetic PII augmentation. Faker generates artificial names, dates of birth, and patient ID to simulate real-world condition. This is fully transparent. The source dataset contains no real PII, so I added them manually to showcase the PDPA concern of this project. Number 3. Anonymization. Synthetic IDs are hashed with HMAC SHA256 using a configurable subkey, and the raw PII columns are dropped. Bucketization. Continuous values like blood pressure and cholesterol are mapped to ACC and AHA categorical labels: normal, elevated, stage 1 hypertension, stage 2 hypertension, and so on. Synthetic clinical note generation. Each row is rendered into a natural language description, which becomes the input for downstream NLP enrichment. Output is a patientmaster.csv, persisted to be a bind-mounted volume, so ingestion can be rerun without repeating the pipeline. Knowledge graph. Ingestion. In ingest, populates Neo4j with 2 interconnected subgraphs. The patient subgraph holds patient nodes connected to symptom, condition, risk factor, age group, and disease nodes via relationships like has symptoms, has condition, has risk, and diagnosed with. The knowledge subgraph holds disease, symptoms, treatments, and guidelines nodes extracted from PDF guidelines through a 3-step process. PDF plumber extracts page text. The page text is chunked into approximately 800 token segments, and Llama 3 extracts triples in the form disease, has symptoms, and disease treated by treatment. A normalization map ensures that synonyms, high BP, HTN, elevated blood pressure, all resolve to the universal node hypertension, keeping both subgraphs joinable, so that I don't have to create a new node every time I run into a new synonym that's describing the exact same thing as the previous nodes. 3-track reasoning, sequential and independent. When a clinician submits a free text case, the 3 tracks fire sequentially but remain independently inspectable. Track 1, Rule Engine. Pure Python Lambda evaluates around 20 deterministic clinical rules from Rule Engine. Each rule has a condition, severity, and message tied to ACC and AHA thresholds. Output is a severity sorted list of alerts. Latency, milliseconds. I better showcase here. Track 2, Similarity Engine. We do not run a black box classifier. Instead, in Similarity Engine, we learn term importance from diagnostic lift. The ratio of how often a term appears in diseased versus non-diseased cases, and we learn numeric feature weights from the mean separation between the two diagnostic groups. The hybrid score combined weighted term Jacquard at 55%, numeric similarity at 35%, and small risk burden boost. Top 3 matches are returned with the full score decomposition. Track 3. Cognitive graph rag. AI rationale. In Cognitive Engine, Llama 3 first extracts symptoms and clinical parameters from the input text with a deterministic regex fallback if the LM fails. Neo4j is then queried for connected subgraph of diseases, treatments, and guidelines reference. Finally, Llama 3 receives a strictly scoped prompt containing only that graph evidence, the rule alerts, and the similar cases, and produce a structured 5-section diagnostic assessment. End-to-end latency. It's recommended to use GPU, but it's also runnable on CPU only. The dashboard surfaces explicit MVP performance verdicts for every track, alerts fired, top similarity scores, graph evidence count, retrieval confidence, so the clinician immediately knows whether each track produced useful evidence or whether grounding was weak. Every reasoning step is also logged to trace JSON with hashed ID only. No raw PII is ever persisted. The limitation is, since this is an MVP, not a clinical certified product, the known limitation is the Jacquard similarity treats all symptoms equally outside the learned weights. Synthetic clinical notes are generated, not authentic narratives. LLM outputs vary across runs. PDF extraction may be noisy. The future work includes the following: a golden test set with known expected outcome, formal retrieval benchmark, optional vector retrieval alongside the graph. The architecture, however, is intentionally extensible. Every track is independently swappable. Thank you.